Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. So today's session is Fundamentals of AC Circuits Part 1. Now let's take the example which I have already discussed once. That is a single turned coil rotating in a magnetic field. So here a pair of magnetic poles are assumed, north, south. This is taken as north for convenience. And the four positions, say position 1, 2, 3, 4. That means this coil is rotating in this magnetic field. And what will be the, let's see what will be the induced EMFs in position 1, 2, 3 and 4 and back to 1. So in position 1, 3, that means the coil is, the plane of the coil is horizontal. So what we are seeing here is the cross section of, this is the cross section of conductor A, this is the cross section of conductor A dash. So we know that the induced EMF in the coil is equal to 2 BLV sin theta volts. The B is the flux density, L is the length of the conductor and the length of one conductor. That means this length is L. This is the N connection which is not considered. So L is the length of the conductor in the magnetic field, V is the linear velocity of the conductor, and theta is the angle between the flux density vector and the linear velocity vector. So now assume the position 1 is the plane of the coil is horizontal. So this is the position 1. That means assume conductor A is in position 1. The plane of the coil is horizontal. Let's see the EMF induced in this position. The coil is rotating in counterclockwise direction. Now, so this is now conductor A is here. This is here, it is A dash. Whatever the voltage induced in conductor A and A dash are identical and 180-degree opposite, it can be added. Or direction is exactly opposite. So the voltages can be added. So here, this is the position of conductor A. It is in position 1. Now see the flux density vector and the linear velocity vectors. Flux density vector is straight up. So here the coil is moving in the counterclockwise direction. The flux is directed from north to south. So this is the direction of flux density. And also here conductor A is moving up. So same is the direction of the velocity vector. Flux density vector and velocity vector both are in the same direction at this position. So theta is equal to 0. So induced EMF is equal to, in the coil is 2 BLV sine theta, which is equal to, since theta is equal to 0, the induced EMF is 0. That is, this is the induced EMF in position 1. Now assume the coil is rotating counterclockwise through an angle of 30 degree. That means A comes here. The coil is rotating in the counterclockwise direction through an angle of 30 degrees. So the conductor A occupies this position. Now let's see what is the angle between flux density and velocity vectors, linear velocity vectors. Flux density, same direction only. That direction of flux density does not change. But here see the direction of velocity vector. So it is tangential to the circular path of the coil. So here it is tangential to the circular path. So this angle between B and V will be 30 degrees now, because here B is perpendicular to this positive x direction. This is the reference direction. From here only we started. So flux density vector is perpendicular to positive x-axis, and linear velocity vector is perpendicular to this, what is that, radius vector r. So the angle between B and V is same as the angle between these two lines, because these two lines are, B is perpendicular to this line and V is perpendicular to the radius vector. So angle between these two lines, 30 degree, will be the same as the angle between their perpendiculars. So this angle also will be 30 degrees. So BLV sine theta. Now the induced EMF at this position is BLV sine 30. That is, this is the induced EMF. So BLV, let's take a 2 BLV is equal to, so BLV sine theta is the induced EMF in a conductor. As for the coil, it is 2 BLV sine theta. Let us assume the 2 BLV is equal to 1. So 2 BLV sine theta is half. What is the magnitude of the induced EMF at this position is 0.5. Because 2 BLV, assume it's equal to 1. Flux density is constant, length of the conductor is constant, and the coil is rotating at a constant velocity. So V is also constant. So assume that 2 BLV is equal to 1. So 1 sine theta is the equation for the induced EMF. Theta is equal to 30 degrees. So induced EMF at this position is 0.5. Now, assume the conductor moves in counterclockwise direction another 60 degrees, so that it is vertical. Plane of the coil is vertical. The conductor A comes here. So conductor A was here and it comes here. Now what is the angle theta? Theta is 90 degree. Now here the velocity vector is tangential to the circular path. Velocity vector is shown here. Flux density vector is always up. So the angle is equal to 90 degrees now. Same as this angle. So BLV sin theta is maximum now. So the induced EMF at this position is 1. Okay. Now assume it is moving further through another 60 degrees. That means the conductor A comes here. So here what is the angle between flux density and velocity vector? It is 150 degrees. This angle is 30 plus 60 plus 60. This is 150 degrees. Same is the angle between V and B and V. So the equation for induced EMF is equal to 1 into sine 150. It's again is equal to 0.5. Now another 30 degrees, the conductor A comes here. A dash will be always opposite to it, at the opposite position. If A is here, A dash will be here. Now what is the angle? It is 180. The angle between B and V is 180 here. So the induced EMF is 0. That is at this position. Assume another 30 degree in the counterclockwise direction. So the total displacement from origin is equal to 210 degrees. Up till here it is, up till this line it is 180, 180 plus 3, that is 210 degrees. So this is the velocity vector. This is the flux density B, V. The angle is 210 degrees. So in the second quadrant, all theta was positive, but this is the third quadrant. So it's 210 degrees here. Value will be negative. That is minus 0.5. That means the direction is opposite now. EMF induced in the conductor A has an opposite direction after 180 degrees. Now the angle between B and V is 210 degrees, sine 210, it's negative. So BLV is equal to, BLV is 1, so 1 into sine 210, that is minus 0.5. So induced EMF is the magnitude, it is marked here. So like that it continues and completes one revolution. When one revolution is completed, the voltage again becomes 0 and the point comes to this position. That means again starting. So this is the EMF induced in the coil, 0 to 360 degrees. So starting point after 30 degrees, after 90 degrees, after 150 degrees, 180 degrees, 210 degrees, this is 270, it's minus 1. Then 330, again back to 360 or 0. So this is one cycle of EM. So when the coil completes one revolution, one cycle of EMF is induced in the coil. When the coil completes one revolution, one cycle of EMF is induced in the coil. So the induced EMF equation is equal to Em sin theta, Em sin omega t or Em sin theta, where omega is the angular velocity. So the coil is, assume the coil is making 50 revolutions in 1 second. 50 revolutions in 1 second. So 50 cycle of EMF is induced in the coil. 50 cycles of EMF is induced in the coil. So one revolution means what is the angle through which the coil or the conductor moves. So when one revolution is complete, the angle through which the conductor moves is 360 degrees, or it's equal to, so in one revolution the conductor moves through 360 degrees, or it's equal to 2 pi radians. 360 degrees equal to 2 pi radians. So 2 pi means 6.28 radians. That is the angular displacement in one revolution. So the conversion normally we use 180 degrees equal to pi radians. 360 degrees 2 pi radians, or 6.3.14 into 2, 6.28 radians. So when it completes 50 revolutions, so the angle through which the coil moves is 50 into 2 pi. So you can write it as 100 pi. 100 to 3.14 into 100, 314 radians. So in 1 second, the coil makes 50 revolutions. So 50 cycles of EMF is induced in the coil. So in one revolution, the coil moves through an angle of 360 degrees, or 2 pi radians, or 6.28 radians. So if it is making, the coil is making 50 revolutions per second, then the angle through which the coil moves in 1 second is 50 into 2 pi radians, or 50 into 2 pi radians, you can solve it to 100 pi radians, or 3.14 into 100, 314 radians. So the angular velocity of the coil is 314 radians per second, or omega is equal to, angular velocity is equal to 314 radians per second. So angular displacement at any time can be found out by multiplying theta is equal to omega t. Omega is the angular velocity, t is the time. So this assume the frequency is 50 cycles per second. Then the time to complete one cycle, the time period, is equal to 1 by 50 seconds. The coil is making 50 revolutions per second. That means the waveform is completing 50 cycles in 1 second. 50 cycles in 1 second. So what is the time to complete one cycle? 1 by 50 seconds. So that means from here to here, the time for the coil to move from this point to this point is 1 by 50 seconds, or 0.02 seconds. So this time period for half cycle, or the time to complete half cycle, is 0.01 seconds. So E is the induced EMF. So we can express it as Em sin omega t, or Em sin theta. Theta is the angular displacement, and omega is the angular velocity, t is the time. So E here, small e, that means the instantaneous voltage. Voltage at any instant is equal to maximum value into sin theta. In our case, 2 BLV, we have taken it as 1. So in our case, the equation can be written as 1 sin theta. E is equal to 1 sin theta. EMF induced in the coil is 1 sin theta. And maximum value is equal to 1. Omega is the angular velocity. We calculated it as 314 radians per second, or it is 2 pi f radians per second. Time period is the time taken to complete one full cycle. That's equal to 1 by f. So 50 cycles in 1 second, or time to complete one cycle is 1 by 50 seconds. 50 cycles in 1 second. So one cycle can complete in 1 by 50 seconds. That is called the time period. Now assume there are two sets of coils, A dash and B dash. When both are identical coils only, they are fixed at an angle, assume at an angle of 30 degrees. And two identical coils fixed at an angle of 30 degrees. And the set of coils are rotating in the counterclockwise direction. Now let's say what is given in figure is the voltage induced in coil B. Now see, in the direction of rotation we are considering it as anti-clockwise. In the direction of rotation, A reaches any position first. Here three positions are marked. 1, 2, 3. Let's take this position as 4. So when the set of coils are rotating in the counterclockwise direction, coil A dash, I'll call it as coil A only. Coil A reaches any position first, then only coil B reaches that particular position. That means when it is rotating in counterclockwise direction, A reaches, say, position 3 or position 4, whatever it is. And after another 30-degree rotation only, coil B reaches that particular position. For example, if we take position 3, coil A reaches position 3 first. Then after another 30-degree rotation of the coil only, coil B reaches that position. That is, coil B will reach position 3. That means the voltages in these coils, their maximums or zeros are not happening at the same instant. Say this is VB, this is VB, whatever is plot, the figure in the figure given, the plot given in the figure is VB, then what will be VA? So VA will be, say this is 30 degree, this duration is 30 degrees, so it will reach VA will reach the maximum, this is maximum. 30 degree before VB reaches. This is the maximum of VB. So VA will be, the waveform will be like this. This is VA. Tell you once more, the set of the coils are rotating in counterclockwise direction. So when the sets are moving in the counterclockwise direction, VA crosses any position first, then only VB. So the voltages induced in these coils also will reach any particular point first. Say for example, zero position, VA reaches first. Then after 30 degree only VB reaches at that point. Then VA reaches maximum first. After another 30 degree only VB reaches that point. So that means there is a phase difference between the voltages induced in these coils. Phase difference. So they are out of phase by an angle of 30 degrees. So if we represents the voltage as RMS phases, then if I take VB in the reference position, the voltage induced in coil A is leading the voltage induced in coil B by an angle of 30 degrees because VA comes to any position first, then only VB. Say, let's take a third coil, identical coil only, C dash. All are fixed together. Say, now, what will be the voltage induced in coil C? So, coil C, the voltage induced, actually C lags behind B only because the set of coils are rotating in counterclockwise direction. A comes first, then B, then only C. That means the voltage can be represented like this. This is Vc. This is Vb. So when the set of coils are rotating in the counterclockwise direction, Va comes first, then Vb, then Vc. That means VA is first, then VB, then VC. So VB is lagging behind VA by an angle of 30 degrees. And VC is lagging behind VB by an angle of 30 degrees. So if you are represent as an RMS phasor, it will be VC will be lagging behind VB by an angle of 30 degrees. So this is what is called phase difference. That means the maximum positions or zero positions are not happening at the same instant. So here there is a 30-degree difference is there. What is the time corresponding to that? Half cycle is one full cycle is zero point 0.02 second. Half cycle is 0.01 seconds. So this 30-degree difference corresponds to a time 0.01 by 6. That is this 0.00167 seconds. That means when the set of coils are rotating in the counterclockwise direction, A comes to position 3 first. Then after a time interval of 0.00167 only, B comes to that position. And further, after another time interval of 0.00167 seconds, C comes to that position. So the voltage maximums or zeros or any corresponding positions are not happening at the same instant, but with a difference. So we are saying that these voltages have a phase difference. So in this case, since we are taking VB as the reference, VA is leading VB by an angle of 30 degrees because VA comes first. VA is leading VB. After VA only VB comes. But what about VC? VC comes after VB. So in this case, it is VC is the RMS phasor. VC is lagging behind VB by an angle of another 30 degrees. So this is what is called phase difference. So these phasors are not, these are the RMS values of this one. RMS value we'll discuss later. So these quantities are not, or these voltages, they in their voltage waveforms, their maximums or zeros are not happening at the same time instant, but with a difference in time. So we say that the voltages are having a phase difference. When we represent these quantities as RMS phases, then VB in reference behind VB we have taken in the reference direction, VA 30 degree leading VB and VC 30 degree lagging behind VB. So A is the most leading, then VB, then VC. This is called a phase difference. Now let's see what is average value of a sinusoidal quantity. Average value can be found by adding all instantaneous values. The instantaneous values are here the induced EMF, take it as E is equal to 1 sin theta. The maximum value is 1. So instantaneous values when theta is 30 degree, the magnitude of the voltage is 0.5. When it is 90 degree, it is 1. When it is 150 degree, again 0.5, 180 degree, 0, like that. So at a different instance, the magnitude of the EMF is different. What is the average? So average can be found by adding all instantaneous values over this interval 0 to pi and dividing it with the interval, that is pi. So as an equation we can represent it as sum of the instantaneous values is integral 0 to pi Em sin theta d theta. Actually it is integral 0 to pi E d theta, or E is equal to Em sin theta. So integral 0 to pi Em sin theta d theta gives the sum of all instantaneous values divided by the interval is pi. So simplifying, it is Em divided by pi into integral sin theta is minus cos theta. Substituting the limits pi and 0, we'll get 2 Em by pi, or 0.637 Em. So somewhere here you can mark 0.637. This is the average value. That means at a different instance, the induced EMF has got different values, but if we consider a half cycle, we can find the average. This is the average value. So average value is 0.637 times the maximum value. The next is RMS value. RMS is root mean square. That is square all the instantaneous values. E square. E square is Em square sin square theta. Then find the mean of that. Mean can be found out by adding all these squares over the interval 0 to pi and dividing it with the interval pi. So this is the square of all the instantaneous values. By you can find out the mean by adding these squares, that is integral 0 to pi. That means we are adding all these squares of instantaneous values into 1 by pi. That means dividing it with the pi to find out the mean. And then find the square root of that. That is root mean square value. So this equation can be simplified to Em is a constant. So Em square by pi into integral 0 to pi 1 minus cos theta by 2. That is sin square theta can be written as 1 minus cos theta by 2. And integrating and substituting the limits, so we'll get it as Em by root 2, or 0.707 Em. This is the root mean square value. So for all practically we use RMS values only for calculations and other things. Next is form factor. What is the form factor for sine wave? It is RMS by average, RMS value by average value. So this voltage RMS value is 0.707 Em and the average value is 0.637. So dividing it, we will get 1.11. So this is the form factor for sine wave. And one more factor is the peak factor, which is called the maximum value by RMS value. 1 divided by 0.707, it is 1.414 or root 2. That is the peak factor. Now next is the polar phasor representation in polar and rectangular form. Say one phasor. So OA is the phasor here. So it's actually OA is equal to magnitude of OA is equal to root of 3 square plus 4 square. OA can be represented in two forms. Say this magnitude is actually 5 square root of 3 square plus 4 square. So representation in polar form is 5 angle 53.13. Also, it's equal to, I can represent it as 3 plus j4. 3 in the positive x direction and 4 in the positive y direction. This j means 3 plus j4. 4 is not in the same direction, but we have to move counterclockwise by an angle of 90 degrees. J is an operator. So from the direction of j, this is the from the direction of 3, the real part, we have to move counterclockwise by an angle of 90 degree and add 4 units. That is what is meant by 3 plus j4. 3 in the positive plus 3, that means in the positive x direction. And from that direction, move counterclockwise and take 4 units. So that is expressed, that can be expressed as 3 plus j4. So this is the representation in rectangular form. This is called polar form. Both are the same phasor only. So OA can be represented as 5 angle 53.13 degrees. That means its magnitude is 5 units. From the positive x direction, you move counterclockwise by an angle of 53.13. Or from the reference direction, this is the reference direction, move an angle of 53.13 in the counterclockwise direction and take 5 units. That is phasor OA. Also, it can be expressed as 3 units in the positive x direction, that is real part, plus move counterclockwise by 90 degree and take 4 units. So 3, it is to be written as 3 plus j4. So this is called a rectangular form and this is called a polar form. Now another quantity. So this is in rectangular form, I'll express it as minus 8 plus j6. Minus 8 means it is not in the positive x direction, the negative x direction. In this direction, you take 8 units. That is minus 8. And in the positive y direction, take 6 units. So minus 8 plus j6. So this, the resultant phasor has a magnitude of square root of 8 square plus 6 square, that is 10. Square root of 8 square plus 64 plus 36, that is 100. Square root is 10. So this is 10 units. If we calculate this angle tan inverse 6 by 8, you will get 36.86. But the phasor is at an angle of 143.13 from the positive x direction or from the reference direction. If this is 36.86, this angle will be 143.13. So the phasor is to be represented as the minus 8 plus j6. In polar form, it is to be expressed as 10 angle 143.13 degrees. That means its magnitude is 10 units. With respect to the positive x direction or with respect to the reference direction, it is at an angle of 143.13 degrees. That is from the positive x direction, move counterclockwise by an angle of 143.13 degree and take 10 units. That is the phasor which is represented by minus 8 plus j6. So minus 8 plus j6 is in the second quadrant. Take another example. This is 8 minus j6. That is 8 in the positive x direction, 6 units in the negative y direction. So from this direction. Here we are moving clockwise by 90 degrees. That is why minus 6. In the first case, that is 3 plus j4, here moved counterclockwise by counterclockwise through an angle of 90 degrees. So it is plus j. Here it is clockwise 90 degrees minus j. So 8 minus j6 is the phasor. Oh, let's represent it as OA. So in polar form, it can be represented as 8, 6. The magnitude is 10 only. Square root of 8 square plus 6 square is 10. So this is 36.86 degree, tan inverse 6 by 8. So 360 minus 36.86 is 323.14 degrees. So polar form OA is equal to 10 angle 323.14 or 10 angle minus 36.86 degree. Both are same. So minus 36.86 means you have to move in the clockwise direction 36.86 degrees. Same position can be reached by moving in the counterclockwise direction through an angle of 323.14 degrees. Because 360 minus 36.86 is 323.14. So the phasor OA can be represented in polar form as 10 angle minus 36.86 or 10 angle 323.14. So that's all for today's session. The continuation of this will be in the next session, that is part 2 of AC fundamentals.